However, this Range-Kooltz method is fast and efficiently using the computer time, but it meets the accuracy issue because you always use the past value to interpolating those polynomials to extract the future values. So it will make the accuracy low. And to solve such accuracy issues, interpolating, extrapolating, we can use the future values to correct our accuracy issue. So we will involve the future value, which past will be n minus 1, current will be n, and the future will be n plus 1, those values. Let's make an example how this multi-step works. So the multi-step, let's use the first order polynomial, which is linear, right? And before, we were using the first order polynomial using the past equations, which is yn plus 1 equals yn plus 2 h over 2 3 fn minus fn minus 1. So that is only use the past value. Then we want to correct. So this is just a prediction, but we want to correct this prediction using some future value, which is yn plus 1, but still using this first order polynomials. Then the linear become this fn plus 1 minus fn divided by hx. So when you integral this yn plus 1 will be equals yn plus the integral from xn to xn plus 1, the fxn yn dx will be this linear part, which is yn plus from xn to xn plus 1, fn plus 1 minus fn divided by h times x dx. Then in the end, after you integral these equations, it becomes yn plus h over 2 fn plus 1 star. Because you don't know what is this fn, you can say this is the star, where you get from the prediction, and then you are trying to correct your accuracy between the interplay and extrapolating using such corrector step. So how it usually works, this multi-step, how it works. So first, it will be using this equation, yn plus 1 equals yn plus h over 2, 3 fn minus fn minus 1. You just use past value to derive this equations. And first step, we will call starter, which we don't know. For example, the minimum n is 1, so y2 equals y1 plus h over 2, 3 f1 minus f0. You know f0, but you don't know what is your f1 and y1, so we need a starter. And usually such starter is Range-Kooltz method to get y1 and f1. After the starter, you can use these equations to predict what is you y2, right? So predict. So yn plus 1 equals yn plus h over 2, 3 fn minus fn minus 1. And using f1, y1, you can get y2. And using y2, you can get y3, y4, y5, etc. However, it has the accuracy issue, so we use a corrector. And the corrector step is yn plus 1 equals to yn plus h over 2, fn plus 1 star. So, okay, when you know, for example, y1, right? You know here is y1, this is y2 equals y1 plus h over 2 f1 plus f2 star. And this f2 star is from the second step, the predict term. Then after that, you further correct what is uy2, right? So after that, you can increment of your independent variable, which is uxn plus 1, and you will scan the whole range. Okay, repeat. And when you repeat, you don't need the starter anymore, so you just repeat 2 to 4 steps until it finish. So this is the multi-step works. You need a starter to start this whole iteration loop. Then you need to predict from the past value. And you use the prediction to correct your current value. Then you increase the independent variables. And you finish, scan the whole range. And as you go higher and higher order of this item Bashford Moulton, this is called item batch. So item Bashford Moulton method. So as you go higher and higher of this method, it will show significant computational efficient as compared to Range-Kutta. Range-Kutta, as you go higher order, you have to, each step you need to evaluate nth order of the function, but for Adam-Bashhold method, you basically just need to evaluate these 2 steps, right? Okay.